So the Newton synthesis that you did last week is not something that you will have to regurgitate. It was something you need to know there's actually a good valid reason for the outcome. What was the outcome of Newton's synthesis? Because that was the important thing for you to, like I said, you want to see that there's a valid reason for it, not just, I don't know, that's what we do. But what was the important outcome?
Shell representation.
Okay, you have a uniform spherical shell of mass. That means it's the same density on that shell. Then if you're inside, there is no gravitational force between it and you. And if you're outside,
the radius.
Well, it's the same as if all of the mass of the shell was concentrated at the center of the shell. And so that allowed you to, I don't know if you got to, did you calculate the acceleration of gravity as you go toward the center of the Earth? No? Okay. Given that I have a whole different game plan for today, I'm not going to do that. I had pretty pictures and stuff in the, I will at least go to the slide on that and talk about it. I won't do it, but I'll talk about it. Dropping audio frames. Well, the sound's going to be garbled from here on because it's dropped 14 seconds worth of the lecture so far. I rebooted everything to try to avoid that. That's disconcerting. Okay, so here's what the Earth actually looks like. Quick question, irrelevant to anything except for curiosity and knowledge. How do we know that the density of the Earth has these discontinuous jumps? You see the picture on the right is graphing density on the vertical axis and depth on the horizontal axis. How do we know we have those discontinuous jumps in density? Actually, is that right? I've got to look at it more closely. Radius, density, yes.
I'm guessing we shot a bunch of sound waves in there.
Okay. All correct except for the we part. Not they either. That would still imply people did it.
Oh, was it like earthquakes?
Yeah, earthquakes. Now they do things like if you are working in geology, you want to find something like what oil is. They will do things like up the ground so that they're putting in the waves. But for checking the center of the Earth, there is some reach to it. A nuclear detonation, that makes a big enough earthquake that it can be used for this too. And so anytime there is an earthquake, all of their sensors are used to try to determine how the waves travel through the Earth. And different densities will result in different speeds for the waves traveling through the Earth. And that's how they can determine this stuff. And so you might have read, like, after the last Korean nuke test, a couple days later, there was an earthquake at the same site. And people were wondering, I haven't heard any definitive answer, was it another much smaller nuke test, or was it actually an earthquake, probably as a result of seismic shifting from the nuclear detonation under the mountain? There is concern that the mountain that they're doing their nuclear test and might collapse because of the test. So that's how they get this information. And it's really interesting. There is a liquid layer in there. You see the orange layer? That's liquid. How in the world do we know it's liquid down there? No one's been there, mind you. No one has ever gotten through the crust of the Earth, which at its thinnest place is about 7 kilometers deep. Here on a continental, it's more like 20, 30 kilometers. No one's ever gotten through it because it gets hot, and we don't have drills that will drill through it. They tried. There's, I think, a project going on right now to try and drill through the crust to get into the upper mantle. Okay, so how do we know there's liquid down there? It's actually not the density. It's a good answer, but it's not the right answer. Right? Good answers are ones that are well thought out.
Is it because of the earthquakes?
I think they don't see
It's the type of wave that travels through a liquid. A solid it will have both shear and pressure waves. A shear wave is a wave that is traveling like this, but displaces like that. A liquid can't have that kind of wave propagate because it's not stiff. You need something that's stiff to have a shear wave. And so there is a region where they don't see any shear waves. And so they know, okay, there is something liquid that's blocking that. They still see the pressure waves, just not the shear waves. And then there's solid in the middle. How in the world do we know there's solid in the middle? You've already blocked the shear waves. It's because the pressure waves, when they get to the surface, the solid-liquid interface, they send waves around the surface, and those waves around the surface then send out secondary waves. So they can see, there's a solid surface in there. So there's a lot of forensics, if you will, in interpreting the waves that come from earthquakes to get this. Now, that's not what I was doing here. This graph here clearly shows that the density is not constant as you go toward the center of the Earth. Much, much more dense here. Oh, now my pin's acting up. Than up there. We decided we will try a new battery again, a second new battery, one that we just purchased before we spend $1 on buying a new stylus, in case you're wondering why I'm using the same stylus instead of having a new one. So, making the approximation that density is constant going through the Earth is grossly wrong. But it's easy for physics calculation. So we're going to do a grossly wrong, well, actually, should we do it? If we say density is constant, then we know that the force of gravity acting on us divided by the mass of me is the acceleration of gravity. And that's going to be equal to g times the mass enclosed times the mass of me over the radius where I'm at, and then this mass of me that's going to cancel. So I can get the g at any depth just by calculating how much mass is enclosed at that depth and dividing by the radius. Oh, I tried to put a square on there, didn't I? You'll see the equation I wrote is an equation of physics. It's just not a force equation. So that will give me the g at any point. Now, what would your first guess be as to what's going to happen to the acceleration of gravity as you move toward the center of the Earth? Okay, so it increases? Decreases. Okay, so it decreases. So if I drop something at the surface of the Earth, it's going to accelerate downward. You're saying the acceleration will slow as it gets towards the center. Now, of course, this is saying that we dug ourselves a perfect hole. How many people have seen the crummy remake of Total Recall?
I've seen parts of it, like the time.
Yeah, the original one with Paul Schwarzenegger. Yeah, I like the original. The remake I thought was kind of lame, but they have a shaft that goes through the center of the Earth, and they get on the elevator, and they go through the center of the Earth and come out on the other side. You guys haven't seen that? Yeah, okay, you see that part. Okay, it's really poor physics. It's really poor physics because they're going through, and they just have normal gravity, and all of a sudden they get to the center and whoop, shifts to the other direction. What would be correct is, as they're going down, their gravity would get smaller and smaller. What you said is exactly correct. And when you get near the center, you're going to be pretty much floating, and at the center you wouldn't be truly floating, and then in the other direction. So you do have to switch around, but it's not just going to be constant until you get in the middle, and then there we go. Get the side. So, by the way, that reminds me of something one step further tangential. You guys seen that movie? Was it Interstellar? Okay. Now, I thought it was, once again, pretty horrible physics for the most part. The physics of when the time dilation when we get close to the black hole and stuff, that was spot on. And the physics of what a black hole, what it actually appears like, well, it's a spherical region you can't see. They made spherical something you could see, so you could have something. Their science advisor for that was Kip Thorne, the person who famously won the year subscription of Penthouse magazine with his bet with Stephen Hawking. he won the Nobel Prize yesterday in physics. Well, he got a quarter of the physics prize for the research that he and others have done on detecting gravitational waves. So it tells you how important it's considered. Last year, I think, was the first detection of gravitational waves. They just announced last week they think they detect gravitational waves, which I think brings it up to 3 they think they detected. Anyway, getting back to this, to finish this up, all I need to really calculate is the mass enclosed to determine what G is, right? Because R squared, the mass enclosed is going to depend on the radius, and I can go from that. Well, we know volume for a sphere is 4/3 pi radius cubed. And so the mass enclosed is going to be my density times the volume. So that's going to be density times 4/3. Well, if the density is constant, the density is going to be mass of the Earth divided by 4/3 pi raised to the Earth cubed. I know that's horrible handwriting. So I'm going to put that in here. It's going to be mass of the Earth over 4/3 pi raised to the Earth cubed. So there's the density. And then volume, 4/3 pi radius cubed. Cancel the 4/3 and pi. So that's how much the mass enclosed at any distance r away from the center of the Earth is going to be. Put that into my equation here, and I have G is equal to capital G times mass of the Earth times radius cubed over radius squared, radius of the Earth cubed. Cancel 2 of those. And there we have it, a linear change. G would just decrease linearly as you go towards the center of the Earth, which once again agrees with what Alex said. Realistically, how is it going to be different from that? Okay, the density is much lower near the surface. If you look at this graph I gave you, out here is the surface, and here's the center. And you notice the density at the surface compared to the density at the center, it's a huge, huge difference. So as you come in, the mass enclosed is not changing very much. And so you could treat it much like everything is constant and R is, decreasing. And so G would actually be getting bigger probably in the beginning portions as you go in. But then pretty soon when you start getting up at higher densities, which you can see when you go from here to here, you've now gone through the crust and it's much more dense, then you'd start dropping off more mass. Okay, so that was the important ideas, the outcomes we wanted to see from that, was why we can use something simple like this and do calculations for gravity. We'll talk about a ball and we say the gravity between that ball, the sun. Force of gravity between the sun and the Earth, we just treat the sun as if all the mass is at the center. That's saying the sun is uniform shells. The density can change as you go in and out. As long as each shell has constant density on the shell, then you can treat it as if all the mass is at the center. And the Earth likewise, except for the crust, which is very thin, it's a minuscule part of the Earth, it's very uniform, so you can do that as well. So that was the important outcome from all of last week's hard work. I did mention, I'll say it again, the rocket experiment report. Remember last time I was here on Tuesday, we went out and we played with the rockets. And you were supposed to write a group report, so group of three, one report for each group, not one report per person. And it was supposed to be due before class today. But I wasn't here last week, and I didn't remind you. I was going to remind you on Monday, but even at that, you probably wouldn't have had time to get together the group and get the report done by today if you hadn't done it already. So I will postpone it till a week from today. right? Make sure everybody has a chance to get a good score on something that should be a simple. What should a report have in it? It should have the experiments you did, changing the water in mine, what you learned, what went wrong, because we clearly had one group, not pointing any fingers, that had something go wrong. So writing up what you learned from playing with the rockets. So it's showing, that it wasn't wasted time, that we were actually learning some things about physics there. It doesn't need to be excessively long. I'm not looking for a 5-page report. But because you want to put your data and have some discussion, I'm looking for at least a page, not just, VVD Vici isn't going to cover it. Okay. I've only spent 15 minutes, so I still got some time. We are going to today work with potential energy and how it relates to forces. So I said in class, I wasn't here last week and I wasn't lecturing. I always am fearful. Did he cover the things that I wanted to cover? Well, I hope he did. But I mentioned yesterday that we define potential energy based on its change. Potential energy isn't defined on its own. It's defined simply as the change of potential energy between point A and point B is minus the work done in moving from point A to point B. And so here I have written out that equation. Work is force dot distance. Dot means parallel. And so for Cartesian coordinates, this here is in Cartesian coordinates. Then dl is dx in the x direction plus dy in the y direction plus dz in the z direction. And the force would be force x in the x direction plus force y in the y direction plus force z in the z direction. So that's how we do that calculation. And we're going to get some experience, lots of experience with that, depending on how far I get into today's work. One of the beautiful things about potential energy is that potential energy is a scalar value. It's not a vector. It doesn't have direction to it. Now, to get it, we had to use some vector calculus. But we have a scalar. It's a lot easier to work with scalar values than with vector values. Then calculating the force, because we did that integral to go from force to potential energy, it turns out that we can do the opposite of the integral. What's the opposite of the integral? Derivative. We can take a directional derivative of the potential energy and find the force vector. So the force vector, that minus sign is, no surprise, because there was a minus sign in the definition of potential energy. The gradient, which is the directional derivative, it's symbolized by that triangle with the point down with a vector sign over it, of the potential energy. And so in Cartesian coordinates again, that's the gradient function. It's the derivative with respect to x. Notice it's a partial. It's a partial derivative with respect to x. What does it mean?
Everything else constant?
Yeah, everything that's not x is going to be constant. So those are the easy derivatives. It's just like saying, okay, this is the beginning derivative that, when you started calculus, there was only one variable, right? And so all your derivatives were essentially the same as a partial derivative then. And then when you get to more complex things, then you have to use things like the chain rule when you have more than one variable. Okay, so let's not go this way. Let's go this way. Potential energies are only defined for conservative forces. Conservative forces, the word conservative we talked about yesterday means that you don't gain or lose anything. So conservative forces, we have a couple definitions here besides that. A conservative force is defined as a force that if it goes over a closed path. So in class yesterday, I used Corso's phone as my example, and I had to move from point A to point B. Well, this definition is if I start here and I go over a closed path and come back to where I started, if the work done by the force is 0, then it was conservative. But if the work done by it was not 0, it was non-conservative. So in this case here, I had force gravity and force normal did no work because we weren't moving parallel to it at any time. So that's really not definitive on them. But as I went around, I was constantly pushing the same direction it was sliding. So I was constantly doing positive work. So when I got back to where I finished, or where I started and finished, my network was positive. So the work done by me was non-conservative. Likewise, the force of friction is always in the direction opposite its travel. So there was a negative work done by friction, once again, not conservative. If you did gravitationally, you lift it up, take it all around, bring it back to where you started, the work done by gravity turns out to be zero, it's conservative. An equivalent, but much harder thing, is the curl. If the curl of the force is zero, then it's conservative. Now that one is a mathematical one. It doesn't require you to make a contrived path, but it's usually going to be harder to do. More math. So we will actually be doing that in just a moment. By just a moment, I mean on the next slide. Determine if the spring force is conservative. So here's the spring force. Minus kx, where x is how much it's been stretched. Question, Alex? No, okay. And there's the curl equation, del cross F is 0. I put an equal sign with a question mark over it because we're going to check to see if it's 0. And then here's the gradient. So del cross F. You guys have experience with cross products? Okay. I have found that cross product work can be confusing to people. Here is the way we do a cross product. We do a determinant, x hat, y hat, z hat for the top row. And then for the second row, we put the x component of the first one. So since del is the first one, it's going to be d dx. The y component in the next column, so d dy, z component, the last one, d dz. And finally, the components of the last one. So for the force in the x direction, it says minus kx squared, or excuse me, minus kx vector. Let's treat this as a one-dimensional, only stretching in one direction rather than a three-dimensional spring, because what's that exactly? I'm not sure. So I'm going to rewrite this as minus kx in the x hat direction. Then it's easy. That's going to be minus kx 0, 0. So now I need to calculate that determinant. Calculating determinants. How many people are comfortable calculating a determinant? 1, 2, maybe 3. Okay, with the determinant, if it's a 2 by 2 determinant, I mean, in high school we learned to do 3 by 3s. We learned to do 2 by 2s. 2 by 2s was real easy. You take the diagonal going down to the right, the product of those, minus the diagonal going down to the left product. That's what you did if it was 2 by 2. If it's 3 by 3, we try to do something like that, but it turns out that what we try to do if it's 3 by 3 fails to go larger. So the rule that always works is you take one row or one column, and I will take this one, the one with the unit vectors, and then you take each element and multiply it by the determinant of its co-matrix. And you're all like, what kind of crazy language is he speaking? The co-matrix of x hat is the matrix I get if I take out the row and column x hat is in. So I'm going to have x hat times the determinant of that for my first term. Now, what is the determinant of that? Yeah, 0. That's easy. Now, the next step is probably the trickiest part of all. You alternate signs. So the next one is going to be minus y hat. You use the Levi-Civita symbol if you want to know what we do in math when we write it out. The Levi-Civita symbol is something you have subscripts, and if you change the subscript by 1, it changes from +1 to -1. It changes back and forth. times the determinant of its comatrix. So the comatrix of y is going to be d dx d dz. And notice I dropped out the column that y hat was in. And then minus kx and 0. Well, if I do that, I have d dx of 0. Well, clearly d dx of 0 is 0. And then d dz of minus kx. What's the derivative with respect to z of minus kx? Since it's a partial, z is the only thing that's not a constant, so minus kx will be considered a constant. And so the derivative constant is 0. So that was 0, 0. Flip the sign again, so it goes back to plus for the last one. Z hat, determinant of its comatrix, d dx, d dy, minus kx and 0. And we see, okay, d dx of 0 is 0. d dy of minus kx, what's that? Still 0. And so it's equal to 0, thus it's conservative. Now, a quick and easy rule on this is if the x direction is only dependent on x, the y direction is only dependent on y, and the z direction is only dependent on z, it's always going to turn out to be 0. So that's a kind of a fun rule. So we determined that the spring force is conservative. So now, since we determined it's conservative, that means we can define a potential energy for it. So let's calculate the spring potential energy. Now, you should have done this in class, but you did it without calculus. You did it with a graph and calculating the area under the graph, right? That's something that should have been done last week. Okay, so we're going to calculate the spring potential energy. So we have potential energy change is equal to minus the work is equal to the integral from A to B of my force so there I wrote it like I did before, kx hat or kx x hat to separate the direction from the variable, dotted with my dl in 3 dimensions. DL is going to be x hat dx plus y hat dy plus z hat dz. First, let's do the dot product. What does the dot product mean? Parallel parts. So we have x hat is parallel to x hat, but it's perpendicular to y hat and z hat. We started off, I think we even had a question on the test, that we have to have mutually perpendicular directions for our coordinates. So if we do this, we have the force is only in the x direction. So when I do the dot product, what am I going to get? I'm still going to leave my integral. What do I get when I do that dot product? Okay, the y hat and z hat terms are going to disappear because there was no y hat or z hat in the force. And so all I'm going to have is minus kx dx. What happens to my x hats? Nothing they cancel. X hat dot x hat is 1. Right, 1 in the x direction multiplied by 1, but taking only the ones that are same direction is 1 times 1 is 1. So x hat dot x hat is just 1. It's a scalar result. So now I just do this integral. You guys are all smart people. What's the integral of kx dx? Okay, so it's minus kx squared over 2, going from A to B. Now that's equal to, oh, I forgot a minus sign. I put the minus sign here, but I did not put it there. Right, minus 4 is equal to minus the integral. And so minus a minus means it's a plus. Right, so this minus, the two minuses gave me the plus. And so my change in potential energy I changed it from A, B to initial and final. So we could have a constant offset, but we just choose to say, let's make that constant offset 0. So potential energy is just red. Thus, potential energy final is 1/2 kx final squared. Potential energy initial is 1/2 kx initial squared. Or potential energy alone is equal to 1/2 kx squared. So that's finding potential energy from a known force. Any questions about how I went through that process? Was it stressful? No, it wasn't, Alex. I disagree with you wholeheartedly. It was stressful going through the curl to make sure that it was a conservative force, mostly because it's not something you've done much with. But doing the integral of minus kx dx, that should not be in stressful realm. I assume you were joking, or would have been.
Oh, that part was not stressful. The curl was stressful.
Yeah, okay. So this part was easy. Now we're going to do one more thing. Let's say that you were given that the potential energy is 1/2 kx squared, and you're asked, what's the force associated with this potential energy? The force is equal to minus the gradient of the potential energy, which is going to be minus x hat d dx plus y hat d dy plus z hat d dz of 1/2 kx squared. So we have three derivatives to take. What is the partial derivative with respect to x of 1/2 kx squared? Derivative with respect to x of this thing. You bring down the 2. 2 over 2 is 1, so you didn't say 1 or 2 over 2. You said kx. Then we're going to have minus y hat. What's the derivative with respect to y of 1/2 kx squared? 0. And minus z hat, derivative with respect to z of 1/2 kx squared. And we recover the same force we started with. And I'm sure you're thinking, well, what's the point of recovering the same force we started with? It's showing that the equations are legit. I thought that you pushed stuff away. My class period was over and I was worried. Okay, so we've done it with a spring. Now let's go to something way harder. Gravitational force. Universal gravitation, force of gravity is minus r hat direction, so I put the minus right, the r hat in the end. G, mass 1, mass 2, over radius squared. So first, to check to see if this is a conservative force. That gravitational force is spherically symmetric. Right, the direction is always toward the center of the Earth. R hat is away from the center of the Earth, so that's why it has the minus sign. So because it's spherically symmetric, we have that R in there. I'm doing this in spherical coordinates. Now, spherical coordinates is probably an area you're weak at. It's an area I'm weak at, okay? And so I gave us that gradient operator in spherical coordinates. You see, it's not nearly as fun. The radial part is fun, but not the other parts. What's the good thing here? How many variables do I have in the force of gravity? Just one, only the radius. So all of the partial derivatives that are not with respect to r are going to give me 0. And so when I do that the cross product, I'm going to have this. When I evaluate it, we've gone through one carefully. This is very much like the last one we did, right? In terms of it has the 2 zeros here and only has one variable. And so when I do the r hat part, that's going to be times 0 because we have 2 zeros in the code matrix. When I do the theta hat part, it's going to be times 0 because I'm going to have only r as my variable in the the first column, but I'm only taking derivatives in theta and phi, I'm going to have for theta hat, I'm going to be taking derivatives with respect to phi of r squared, 1 of r squared, and with respect to r of 0. And likewise with my phi hat direction. I didn't write it all out because I do only have 13 minutes left. But you can go through and by the same cross product method as above, it's equal to 0. So it's conservative. Huzzah, hooray. Now let's find the equation for gravitational potential energy. In spherical coordinates, DL is once again a lot more complicated. DL has stuff with d theta and with d phi in it. Fortunately, work is integral force dot dl. Our force is only in which direction? In the r hat direction. So that means the theta hat and the phi hat parts, when I do the dot product with force, those are going to give us zeros. And so when I do the integral for the force, I have this long sticking integral. Change in potential energy is equal to minus integral from A to B of I have this, but it simplifies out to G M1 M2 over R squared dr. What happened to my minus signs? Minus times a minus is a plus. What happened to my d theta and d phi? Wait, well, not cancel, but when you dotted with the r hat, there was nothing in the theta or phi, so that's where they disappeared. So now we just do this integral. Not a terribly hard integral again. What do you get when you integrate 1 over r squared dr?
Minus 1 over r.
And once again, I'll change it from x initial to x final. And so that means that I'm going to have potential energy final minus potential energy initial is equal to minus G M1 M2 over R, or I should have made that R's, not X's. That. Once again, we can have a constant offset, but we choose to make that constant offset 0 and identify that potential energy due to gravity is equal to minus G mass 1 mass 2 over R. There's a minus sign. Potential energy is always minus because radius goes from 0 to infinity. Spectrum can have always negative potential energy.
No, because you have to lose it, right? Because it turns into kinetic.
Okay.
Wouldn't it always be negative? I mean, you'd have like a positive potential energy. Well, you can't really, because like if you have an energy drop in, and then once it reaches, it's like constantly losing its potential and its kinetic energy. And once it hits, it no longer has kinetic energy, but it doesn't have like the same potential. It doesn't gain back its potential energy. So that would make sense. That it'd be negative.
I'm not sure I followed every piece of that. But you were thinking good. The potential energy was defined only by its change. What is important is what happens to potential energy. If I start with it up here and I let it come down here, what happens to gravitational potential energy? It lost it, right? So with this form, it's a negative. I start with a negative here, it comes down here. What happens to the magnitude of 1 over r if r is smaller? Magnitude gets bigger. So I have a negative number that got bigger. If the negative number gets bigger, that's if I go from minus 1 to minus 2, it went up or down. It went down. So the potential energy still dropped as it went down. Now it's going to turn out, if we look at things like calculations for orbits, you have the total mechanical energy is the kinetic energy plus the potential energy. If the total energy is negative, then it's going to be bound. It's going to stay orbited. If the total energy is 0 or greater, that means you have enough kinetic energy that it can fly free. It's the same thing if you're working in chemistry. You talk about the energy of an atom with its electronic states. If the energy for an electron is greater than 0, that electron is free to go. If it's less than 0, it's bound. Same ideas. So the potential energy being negative here is not a problem because we define the potential energy only by a change. And so the direction of the change was really important, but the fact that it's the negative number, not a big deal. So we have found the potential energy due to gravity. If I want to find the force from this, I can reverse it. Because I only have 7 minutes, I'm actually not going to reverse it. Right? I can reverse it by just doing the gradient of the potential energy. I just have r hat times the derivative of this. Derivative of 1 over r is minus 1 over r squared. Get back to it. Instead, let's go to an unknown force. Now we're going to apply. On the test, you're most likely to have something that comes from today's lecture. And it's most likely. I'm not saying it's going to, but it's most likely to be something like this slide or the next slide. You're given a force that you're not familiar with and asks if it is conservative, find the potential energy, or you're given potential energy and told to find the force. Right? It's most likely going to be one of those two.
What is?
The test question is the calculus-based question of the test next week.
Oh,
So we look at this, and we have the question, is this conservative? How do I determine if it's conservative? I do the curl of it. So this is in Cartesian coordinates, so that's good. We can do the Cartesian coordinate curl. So is del cross F equal to 0? Well, that's not a del, that's a delta. All right. X hat times, what's the comatrix of X hat? I want somebody to blurt stuff out.
under that is
Z and then minus 0y. Okay, perfect. Next, I put the minus sign because you alternate signs. What's the code matrix of y hat? Somebody besides the first row, since they were the two that answered for the x hat.
Partial derivative of it. Partial derivative of Z.
And down below.
AX squared. And C1.
And finally, somebody that's not Alex to the front row, plus, because I'm shifting the sign back, z hat, and what's the co-matrix of z hat?
du dx and du dy ax squared and negative by.
Okay. Looks like we've got that because no one made any mistakes the whole way through. We got all the two people involved. Excellent. Now I evaluate these. With respect to y of cy. Wrong color. That's not 0, right? That's going to be c. Now for the next one, make sure you do the derivative first. It's got to go top to bottom. You can't go bottom to top. And so d dz of minus b over y, that is 0. Well, that's not 0. I can stop right now because in the x direction, it's not 0. Right? Doesn't the y and c's can't correct that the x direction was not 0. But I'm going to do it anyway. So d dx of cy is 0. And d dz of ax squared is 0. So the y was 0. d dx of minus b over y is 0. d dy of ax squared is 0. Those were 0, but this one was not. And thus, it's not conservative. If I said find the potential energy, how would you respond? You cannot. There is no potential energy defined for it. So why would I do a calculation if there is nothing defined?
Okay, so I just don't know where that C came from.
Okay, d dy of cy.
So we're just taking the derivative of CY.
Right, you're doing the determinant, you're doing this to that and that to that. And it's negative for the one that's going down to the left.
I feel sure because all the other ones we did.
Yeah, all the rest are zeros. Yeah. Good question.
Y just considered constant.
When you're doing a partial with respect to z, then y is a constant. If you're doing a partial with respect to z, anything that's not z is a constant.
Okay.
That's why I love partials. They're just easier. Okay, so that was not conservative. We can't go on and find a potential energy associated with that. This was my last slide. We only have 1 minute, so we're not going to calculate the potential energy associated with this. But you can see that this would require 3 separate integrals because it has an x component, a y component, and a z component. And so you can go through and you can do that integral and find potential energy associated with this.
The second one?
This is different from the last one because I changed the variables so it's CZ in Z direction instead of CY in Z direction.
This one will actually give a 0 and find potential energy squared.
Well, yeah, the curl of this is 0 and then you can find potential energy.